Thanks for the invitation. I'm really pleased to present the results of our study here. And the presentation of today will be about Ultramafic-hosted VMS deposits and why we think this type of VMS deposit is an overlooked subclass of VMS deposits that are forming in complex tectonic environments. So before talking about VMS deposit, I will make about Ultramafic-hosted VMS deposit. I will make a quick introduction about classic VMS deposits, and to do so, I need to talk about the oceanic crust and fluid circulation within the oceanic crust. So here we have a nice little schematic of the oceanic crust with the volcanic section, the transitional zone, the Shittidax, and the plutonic complex. And as you know, the oceanic crust is a very important place where you have extensive heat and chemical exchanges between the crust and the oceans. And most of these exchanges is happening at mid-oceanic ridges. And what's happening is you have seawater circulation within the crust, especially in the volcanic section. But some of this seawater is percolating quite deep within the oceanic crust into the lower Shittidax complex. Here it's getting heated. It starts to be up to 350 degrees and start to leach the metals from the host rocks. And eventually these hydrothermal fluids, which are buoyant, they rise to the seafloor where they are venting. And when they are venting, there you have the formation of these very nice black smokers and also the formation of VMS deposits. So VMS deposits are really the expression of this whole hydrothermal fluid circulation that's happening within the seafloor. And this type of deposits are mined on land, such as this deposit, the Skyotissa VMS deposit, which is a very famous one from Cyprus. And so VMS deposits, they form in many different types of environment, actually, ranging from mid-oceanic ridges, fast-spreading mid-oceanic ridges, slow-spreading mid-oceanic ridges to ultra-slow-spreading mid-oceanic ridges, which are the one we're interested in today. But you can also find them in supra-subduction zone environments, such as fore-arc environment, transitional arc, and also into back-arc environment. And after exhumation, you eventually find these deposits within ophiolites, where they're eventually mined for commodities. And they're generally mined for copper, zinc, and lead, as Joe previously talked briefly about. For the zinc lead type, this is more the SEDEX ones, for example. But the VMS deposits per se are more copper rich and zinc copper in this range of these ternary diagrams. And interestingly, some of them also enrich in precious metals such as gold and silver, as we can see on these ternary diagrams. This is for Canadian VMS deposits. And the reason why of some of these VMS deposits are enriched in gold is mostly related to processes happening in supra-subduction environments that we will not talk too much about today. But what we will be focusing on really today is about these VMS deposits that form in slow to ultra-slow spreading environment. And actually the tectonic environments in which they form are a bit more complex than previously thought. So what are these ultramafic VMS deposits? So as the name say, they are hosted in ultramafic rocks. These ultramafic rocks are generally extensively serpentinized. They're also associated with low angle detachment faults. So for example, in mid-oceanic rich environment, these are oceanic core complexes. But as we are going to see in ocean and continent transition, this can be associated with low detachment faults in hyperextended margins. And these deposits, they are enriched in copper, zinc, gold, and silver, similarly to the classic VMS deposits, but they're also enriched in cobalt and nickel, which is quite unusual for VMS deposits. So here we have a little diagrams or a cartoon that shows you a bit the genetic evolution of this type of deposits. So we have, let's say, an oceanic core complex with the detachment fault. You have this high temperature hydrothermal fluid circulation. During this high temperature fluid circulation, you will have serpentinization. The metals will be mobilized from this area. And when the hydrothermal fluid will vent on the seafloor, you will have the formation of these ultramafic VMS deposits. But because this is a quite dynamic tectonic environment, the VMS deposit can be reworked. They're often bended, they can be brecciated, they lose a lot of their primary features, and sometimes they can be overprinted by lower temperature alteration features. And lastly, also, they can be associated with high angle normal faults that develop during the latest stage of an oceanic core complex. Okay, but so the main question that we have from this review of VMS deposit is that there are two questions that we asked ourselves, or it's like, why are these VMS deposits overlooked? And there's two reasons for that. The first one is that they're forming in complex tectonic environments, as I've said. And the other thing is that this deposit can be easily misinterpreted. So when we say complex tectonic environment, what we realize is from doing the review of more than 60 ore deposits from the geological record, we found that actually some of these deposits are forming in mid-oceanic ridges, which is quite familiar, well known. But some other are kind of forming in ocean-continent transition, and some are forming in supra-subduction zone environment. And we are quite surprised by this type of environment. And the other reason also why we are interested in these deposits is that they can be easily misinterpreted. And the reason for that is that because they're hosted in ultramafic rocks, often you can think that these are kind of magmatic nickel copper PG deposits that have been overprinted by hydrothermal field circulation. And so they're kind of overlooked, or people don't really look into them. And we think that's a shame a bit, because they can represent untapped mineral resources. So really, when we look at these deposits and when we want to do a good classification of this deposit, we need to look at two things. One is the tectonic environments in which they forms, and the second one is really the metallogenic characterization of these deposits. Okay, so here is the map of different ultramafic deposits worldwide. And so actually we know most of them from the seafloor environment. So for example, mid-Atlantic ridges environment, such as here the Rainbow, Logatchev, Semenov, and Nibelungen. And we have also more recently discovered some in the central Indian Ridge or in the southwest Indian Ridge. And so most of our knowledge comes from these seafloor Ultramafic-hosted VMS deposits, which are really great, but also there's a kind of a problem with this type of deposit, is that they only give us a kind of superficial environment of the system. And also they kind of give a bias onto mid-oceanic ridge environment. And they don't show very good insight into other type of tectonic environments. Interestingly, there are two sites which are not directly related to mid-oceanic ridges. One is the BB and Van Damme hydrothermal systems here, and also one IODP drill core within the West Iberian margin, which has encountered sulfide mineralization, which is ODP 173. And these are more related to hyperextended margins, at least for the ODP 173. And so all the other points here on the map are the localities that we have been reviewing. And some of them have been actually very well studied already, such as the Outokumpu mining district here, with this very nice paper by Peltonen et al. 2008. There's also the Maineral fault deposits with this paper from Melekes Tseva 2013, and also the Platanapes from the Alps from Kolta et al. 2019. And so we have reviewed and compiled all these deposits, and from this compilation, we try to characterize really what are the key parameters to understand the tectonic environment, and also which are the key parameters to characterize any given type of massive sulfide deposit as an ultramafic-hosted VMS deposit. So we'll be looking first at the tectonic part of the characterization. So we first look at some geological considerations. So these deposits are always hosted in euphylitic sequences. And so we were looking at the type of ophiolites they are hosted in. So we have, let's say, the classic type of ophiolite or penrose type, but you cannot speak of penrose ophiolite when you're looking at slow to ultra slow spreading settings. But for example, one case would be the Troodos ophiolite from here, which is the most penrose type of ophiolite you can think of. But what's interesting in Troodos ophiolite is that in the southwestern part of the ophiolite, you have what's called the Lima salt complex. And this Lima salt complex is characterized by ultramafic bodies with detachment faults, and close to the detachment faults, you have extensive serpentinization, and next to them, you have also mineralization that really fit ultramafic-hosted VMS deposits. So this type of penrose type of ophiolite are more related to intraoceanic environments, such as mid-oceanic ridges, or perhaps some supra-subduction zone environments. But then you have other type of ophiolites, which are more dismembered or discontinuous ophiolite. One nice example would be the Central Alps or the Western Alps or the Ligurites in Italy. These ones are like slices of ophiolites, which are often composed of ultramafic bodies. And these are embedded within sedimentary sequences, which can be syn-rift or post-rift sedimentary sequences. And these kind of ophiolites are more related to ocean-continent transitions. Also, we take in consideration structural and stratigraphic features, such as, for example, what's present in the hanging wall of the detachment. So most of the time you have volcanic rocks, but sometimes you can have syn-rift sediments, and also you can have the presence of olistostrums. And the nature of these olistostrums, sorry for the word, can tell us some information about the tectonic environment in which they form, if you have volcanic rocks or if you have sedimentary rocks. And so all in all, we can have the first hint about the tectonic environment in which these deposits form. And then the second way we look into that is to look at geochemical features, and especially at the geochemistry of volcanic rocks, which are associated with these ultramafic bodies, which are hosted the deposits. And so here is
Sorry to interrupt you, I have 10 minutes now.
Okay, thanks a lot. And so, for example, here we have some basic diagrams. So this is vanadium versus titanium for the volcanic rocks. And we can see there's a lot of data, I apologize, but we can see some of them are clustering here, which is more related to island arc twilights or even some boninitic affinities. Some of the morbs are here. The gray squares, this is for a typical morb environment from the seafloor. And then you have more OCT environments, which are the blue ones here. So we can see different geochemical characterizations. And we do also the same for chromite composition within the ultramafic rocks that are hosted the deposits. And once again, we can also have a better classification. So here is the titanium versus aluminum. And we can see some environments which are plotting in morb field versus other ones which are plotting within the suprasubduction field. And so when we integrate everything together, that helps us to characterize if we're dealing with a typical mid-oceanic ridge environment, a typical OCT environment, or suprasubduction environment. And what's also interesting is that sometimes we have environments which are a bit overlapping between environments, settings, and then there are sometimes OCT to suprasubduction zones. So it's a bit complex, and we're actually still working on that. So that's why we really think it's complex environments. Okay, so now briefly, I will talk about the features that really help us to characterize these deposits as Ultramafic-hosted VMS deposits. So the first thing, of course, is the host rock. So you have to be hosted in an ultramafic rocks, which is mostly Horsburgite and Dunite, but these ultramafic rocks can be cross-cutted by gabbros or dikes, because during this tectonic exhumation, you have often still some magmatic activity that can actually provide the heat to the system. And you always have extensive serpentinization. So it's very important also is the alteration halo around these deposits. So serpentinization, but what's also common is that you have this overprinting of magnesium, calcium, silicium, or carbon metasomatism, such as ophicalcite and talc. And also very important, you have strong brecciation and deformation. And then finally, what is also very important is the structural control. You're most of the time associated with detachment fault and within the footwall of this detachment fault, but sometimes you can also be within the high angled faults that develops within this detachment fault. So for example, in oceanic core complexes. So here, for example, we have a schematic from the main area fault with the Dergamish deposit. So here you have the detachment fault in red. In green, you have the serpentinite or the ultramafic rocks, which are poorly serpentinized. And in light green here, you have the extensively serpentinized and brecciated host rock. And here you have the deposits. And on the other side of the detachment, in the hanging wall, you have the volcanic rocks and some sedimentary rocks. Sorry, the other way around. And here, this is a cross-section where you can see that the mineralization is really hosted in these extensively serpentinized and deformed brecciated and ultramafic rocks. Some of the problem we faced also is that these deposits are placed into orogenies, and then they are strongly deformed and metamorphosed, and then it makes it really hard to interpret these deposits. And that's, for example, the case for the Outokumpu deposits, where you have, it's much hard to characterize the detachment faults and the alteration features. Also, what's important is the mineralogy and the texture of the ores, for example. So they have overall similar textures than classic VMS deposits. So they tend to be massive. They also have stockwork textures, vein textures. But on top of that, they're often banded, tabular, brecciate, or clastic. And they have actually a bit different mineralogy than classic VMS deposits. They're dominated by pyrrhotite, chalcopyrite, cubonite, solarite, and pyrite. And they have also common nickel cobalt bearing minerals such as cobalt pentlandite and nickel cobalt sulforsenite and arsenide. And this is important because these actually they're mostly present in suprasubduction zone environment, which is a bit surprising. So for example, here we have the cobaltite, pyrrhotite, chalcopyrite. And also this mineralogical textures is very characteristic for it's very similar to magmatic nickel copper PG deposits, and that's why it's easy to misinterpret them as magmatic nickel copper PG deposits. So now the final part of the presentation is about the metal endowment of this VMS deposit. So if we look at these ternary diagrams for the copper, lead, and zinc, we can see that when we compile all these deposits, they are mostly copper rich. Some of them are copper zinc rich deposits. And here, if we look for the gold, base metal, silver diagrams, they're actually not so gold rich, which is a bit surprising because from the seafloor, these tend to be quite gold rich. And possibly what's more interesting is the nickel and the cobalt concentration of these deposits is that in OCT and suprasubduction zone environment, we tend to have higher nickel and cobalt enrichment than in typical midocynic rich environment, which makes them interesting for further exploration. And finally, why we think this deposit might represent potential new mineral resources is then when we actually plot all the tonnage of the known deposits versus when we make a ranking system actually for these deposits, as we can see on this diagram. And we use this zip flow deposit distribution. When any given type of deposit is well explored, then we find most of the type of deposits. The ranking should fit kind of this zip flow distribution. And what we see for our deposit is that we have a lot of gap within our ranking system here, which suggests that there's still some of this deposit to be discovered in the geological record. And then maybe that should drive further exploration. And the reason we think they're underexplored is that any given, when geochemical or exploration companies go for exploration of VMS deposit, they don't go for ultramafic rocks. They go for mafic or felsic rocks, which are the classical alteration, but they don't go for ultramafic rocks that have been serpentinized. That's definitely not your target when you go for VMS deposits. And so we think that we need proper exploration method or models, and also better genetic models to understand how this deposit forms. And finally, here that shows the tonnage and the grades of the deposits compared to classic VMS deposits, which are shown in as these gray crosses in the background. And we can see overall they kind of have the same distribution in terms of tonnage. They might be a bit less endowed in metals, but that's still significant. And so then I come to the conclusions. So what we have seen is that these deposits form in complex environments, so midocynic rich OCT and suprasubduction zone environments, so more complex than what we previously thought. They have a very particular iteration pattern, structural control, and metal endowment, which allow us to distinguish them from typical magmatic nickel copper PG deposits or more mafic type VMS deposits. And then finally, they can represent potentially untapped mineral resources, but we need better exploration models for this type of deposits. And finally, what's interesting is that on the seafloor, we see most of them in midocynic rich environments, but not so much in OCT and suprasubduction environment. So it would be nice to do further exploration in this type of environment to see if we don't find more or a new type of ultramafic-hosted hydrothermal system. Yeah, thank you for your